In this video, the second part of the lecture, I will be talking to you about the method of short truth tables. So suppose we wanted to test the validity of the following argument, which we came across earlier. Here is the argument. If God exists, then there is no evil in the world unless God is unjust or not omnipotent or not omniscient. But if God exists, then he is none of these, and there's also evil in the world. So we conclude that God does not exist. So this is a very complicated argument. There's a lot happening in it. And suppose we wanted to use our tools of our precise formal logic to try to test whether or not it's a good, deductively valid argument. So the very first thing we have to do is we have to translate it. So this goes back to the last part of this unit where we focused on the translation of uh, English sentences into our formal logic. So the first thing we do when we're faced with an argument in a natural language is we translate it into our formal language. And we can translate it as follows. So I haven't listed it explicitly here, but as a part of our translation, we have a translation manual which tells us which simple atomic sentence letters correspond to which simple sentences. So for instance, G here stands for God exists, and E stands for there is evil in the world, and J, O, and K stand for God is just, God is omnipotent, and God is omniscient, respectively. So given that translation manual, we have the argument which we have with three premises. So first, if G, then not E, or not J, or not O, or not K. So if God exists, then um, there is no evil in the world unless it's not the case that he's just, or it's not the case that he's omniscient, or it's not the case that he is omnipotent. Premise two, if God exists, then he is all of those three things. He is just, omnipotent, and omniscient. Now, premise three, we say there is evil in the world, and then we conclude from these three premises that there is no God. So I'm not concerned with whether or not this argument is sound. That is, I'm not concerned with showing you right now. With deciding or trying to tell you whether or not God in fact exists, this is not relevant to the class. But what we do care about, or what we can use our tools of logic to show, is whether this is a valid argument, which is to say that if these three premises are true, then we can conclude that there is no God. But of course, even when we figure out whether this is valid or not, we can still then debate about whether or not these premises are true. So you might think that, for instance, premise 3 is false, that in fact there isn't evil in the world. There just seems to be to our finite minds. In any case, the final thing I want to note about this argument translation is that in the previous lecture, far back when I provided a translation of this, I think I included only two premises where I put E as a conjunct with this conditional here. But here in this translation, it's a bit more clear, where even though we have this sentence here, if God exists and he is none of these, and there's evil in the world, we have a single sentence, but we can still turn that one sentence into two premises. So we have the sentence, if God exists, then he is none of these, i.e. he is just, omnipotent, and omniscient. And there is evil in the world. We translate that by giving two premises. First of these premises is that if God exists, then he is all three of those things. And as its own premise, we have the claim that there is, in fact, evil in the world. Okay, now that we have this translation, and hopefully you can see how it respectfully translates this argument, We can now think about creating a truth table to, evaluate whether all rows on which the three premises are true are also rows in which the conclusion is true. But since there are 5 atomic sentences between the premises and the conclusion, if we constructed a full truth table, we would need 2 to the power 5 rows, which is 32 rows. So actually constructing a full truth table for this argument here would be very, very challenging and take a lot of work, and be, annoying to have to do all that work. And I'm not going to ask you to do all of that work of creating truth tables with, for instance, 32 rows. So we should avoid doing so. And thankfully, there are ways of getting around that. So with arguments where, for instance, there's only 2 or 3 atomic sentences, it's simple enough to create a truth table because at most we have 8 rows. So these techniques I'm teaching you now in this lecture and also in the lecture before, they don't really matter that much if we do not have very, very complex arguments or sentences. But once we start having very complex and long arguments or sentences, this technique here of avoiding creating complete truth tables becomes important. So in the reading for today, it talked about how you can show that an argument is invalid by constructing only a single line of a truth table, that on which all the premises are true and the conclusion is false. Sorry, there's a typo there that should say is false. So let me repeat that. In the reading, it talked about how you can show that an argument is invalid by simply creating a single row or line of a truth table on which all of the premises are true and the conclusion is false, because just a single row like that is enough to show that the argument is invalid, because invalidity only requires that it's possible that all the premises are true and the conclusion false. The reading then says that to show that an argument is valid, you must nonetheless construct a complete truth table to show that every valuation or every line or row is such that one of the premises is false or the conclusion is false. So the reading says that actually to verify whether an argument is valid, you do have to construct a complete truth table. So that means that we would have to construct a complete truth table with 32 rows. But I want you to think about this, that consider what happens if you try to construct a row on which all the premises are true and the conclusion is false, but you find that it's impossible to construct such a row. Now, if that turns out to be that way, then you can show that the argument is valid without constructing an entire complete truth table. So this method I'm going to show you now is a way of establishing that arguments are valid without creating entire truth tables. And before I get into the details of how the method works, and then I'll work through an example just from a distance, how the method works is that you try constructing a row on which all the premises are true and the conclusion is false. So you try showing that the argument is invalid, but then if you find that it's impossible to create a line on which all the premises are true and the conclusion is false, then you know that the argument is valid, because you know that every row has to be one on which either one of the premises is false or the conclusion is false. So let me now turn to the method and then an example of it. So the first step of this method is that you start with the assumption that all of the premises are true and the conclusion is false. This can be represented as a single row of a joint truth table where all the premises have T under their main connective and the conclusion has an F under its main connective. Then, by reasoning backwards using the meanings of the connectives, you can determine what the constituent formulas must have as their truth values. That is, you fill out the rest of the truth table working backwards from having t's under the main connectives of the premises and having false under the main connective of the conclusion. By working backwards in that way, you will eventually reach one of the following two conclusions. 1. You will find a valuation, i.e. a row of the truth table, on which all the premises P1 to Pn are true and the conclusion C is false. In this case, you've shown that the argument is actually invalid, that it's not valid. You've found a row which shows that the premises may be true while the conclusion false. So here you can kind of simply note that you've shown that this row establishes that the argument is valid. But the second possibility is that you discover that there is no possible way of making the premises all true and the conclusion false. So you must be clear to yourself that you've exhausted all the possible cases before concluding that the argument is valid. So this can be rather involved, but as we work through the example with this argument here, we'll see how this works. Okay, so recall our translated argument, and now instead of me writing out a complete truth table with 32 valuations, I'm going to use this method that I've just given you, the short method. So the first step is that we assume the premises are all true and the conclusion is false. So what that looks like is as follows. Here we have in each main row each of the premises and the conclusion. And what we do is we write under the main connective of each premise a t to indicate that we're assuming that all the premises are true. And then we write under the main connective of the conclusion that we are assuming that the conclusion is false. And now I have a t under this occurrence of E here because the third premise is simply E itself. So assuming that all the premises are true, we assume that E is true. And so we know that the occurrence of E in the other premises will also have to be true. So now what we do is we start working backwards to fill out the rest of the table given our knowledge of how the connectives work. So since the conclusion not G is false, by the meaning of negation, we know that G is true. So what we do is since we know not G is false, we know that G has to be true. So we put a true under G and then put a true under the other occurrences of G throughout the premises. Third, the second premise is a conditional that we know is true, this one here. So we assume that this premise is true, this conditional is true. And furthermore, from this second step, we know that the antecedent is true. So therefore, if we have a true conditional with a true antecedent, it must be that the consequent is true, because how the conditional works is that it's false when the antecedent is true and the consequent is false. So we know that this consequent of this conditional has to be true. And since this consequent is a conjunction requires all of its conjuncts to be true as well. So here note also that I've omitted the parentheses around either J and O or O and K because as we know, whichever way you put the parentheses is going to be equivalent. So as a convenience, I've omitted the parentheses. But we know that since this consequent J and O and K is true, by the meaning of conjunction, we know that each of the conjuncts J, O, K have to themselves be true. So we put little t's under all of them. And then we can also put t's under the occurrences of those three sentence letters in the other premise. Now, fourth, let's inspect the first premise since the rest of the argument has been filled out. So, given the meaning of negation and disjunction, we can fill out the consequent of the first premise. So, since we know that J, O, and K are true, we know that their negations are false. And here we have a disjunction of three sentences. We have a disjunction which each disjunct is as follows. We have not J, not O, and not K. And just like with the conjunct here with three conjuncts, here with the disjunction, we haven't bothered putting in brackets to disambiguate it because we know that whichever way we use brackets will be equivalent. So for convenience, you can just note that here we have a disjunction with three disjuncts. The three disjuncts are not J, not O, and not K. And we know each of those disjuncts is false because J, O, and K are true. So we put false under the negations of J, O, and K. And then we know that a disjunction requires that at least one of its disjuncts is true. So because none of these are true, we know that the disjunction is false. Now, since we assumed E is true, because it's the final premise, so we assume it's true, we can now fill out the rest of the argument. So because E is true, we know that it's true under here, and we know that its negation is false. So this entire consequent here of this conditional, which is the first premise, the entire consequent of that conditional is a disjunction between not E, which we know is false, and not J or not O or not K, which we also know is false. So this disjunction here is false. And now we have a conditional. So note finally that we've filled this out. We note that here in the first premise, we have a conditional which has a false consequent and a true antecedent. And we know how conditionals work is that when we have a true antecedent and a false consequent, the conditional is false. So we have to put a false under the conditional here. But we also assumed that this conditional was true because this conditional, if G, then not E or not J or not O or not K, that entire conditional is the first premise. And as we started with the very first step, we assume all the premises are true and the conclusion is false. But then what we've shown by unpacking that assumption that actually the first premise cannot be true, that it has to be false. So that means that we've found a contradiction. That is, we've found that it's impossible to construct a line of the truth table on which all the premises are true and the conclusion is false, because in order to create such a line, we need to have the first premise be both true and false. So our assumption that the premises are all true and the conclusion is false led to a contradiction. It's impossible for that to hold. So the assumption that all the premises are true and the conclusion is false cannot be true, which is to say that the argument is a valid argument. That is to say that there can be no row of the truth table on which all the premises are true and the conclusion is false. So some final remarks is that you can use a similar method as this for the other semantic notions. So for instance, to show that a sentence is a tautology, what you can do is you can try to construct a row of a truth table on which it is false. Then if you find that it's impossible to construct a row of its truth table on which the sentence is false, then you know the sentence is a tautology because you know it's impossible for any row of that truth table to be one on which the entire sentence is false. Or another example is that to show that two sentences are equivalent, what you can do is you can try to construct a row of their joint truth table on which they differ in truth value. But if that cannot be done, then they are equivalent. And in order to apply this method, it goes back to something we mentioned in the overall short truth table method, which is that you have to exhaust all possible cases. What does that mean? Let's go back to thinking about how we can apply this method to show that two sentences are equivalent. So again, what you do is you try to construct a row in which they differ in truth value. But you have to note that there are two different ways in which two sentences can differ in truth value. The two different ways are as follows. The first sentence is true and the second sentence is false, or the first sentence is false and the second sentence is true. So to show that two sentences are equivalent using this method, here you have to try to construct a row on which the first is true and the second is false, and you have to show that it's impossible to construct such a row. Then you have to start again and try to construct a row in which the first is false and the second true, and show that that other case is impossible. So you have to work through both cases to show that in both cases in which the two sentences differ in truth value, it's impossible to construct such a row. And if that all cannot be done, then you've shown that the sentences are equivalent without having to construct an entire truth table.